Hello, welcome to week 8. This week we're going to continue to talk about probability and also move into a little bit of random sampling as we continue talking about 7th grade. There's a few pieces that we didn't really get to last week. I'd like to talk some more about compound events and more specifically about simulating compound events. In your homework you probably noticed that the first of the listed assignments, the waiting times problem, was really challenging and pretty difficult. This problem is very complex and something that typically isn't worked on until AP stats in high school or even college statistics on a theoretical level. So the expectation in 7th grade is it's just that they can set up a simulation and do an experiment, collect data, and see what kind of extrapolation, I guess, they can come up with for answers for this. But even just designing this can be challenging. So we're going to talk about this one. I don't know if you guys had a chance to already look at the solutions page. Hopefully if you were so frustrated with this problem in doing homework, you looked at the illustrative math page and got some ideas for how to move forward with this problem. That's probably what I would have done if I was stuck. So let's take a Actually, before looking at that other problem, I wanted to show this simpler version of another task, asking students to use a simulation to determine a probability. So this one is earlier on in the school year. It's a lot simpler. It sets up the process and guides them through it pretty nicely. So the task here: roll 2 dice 10 times. After each roll, note whether any 6s were observed and record your results in the table below. So students can do that, and then they are asked to answer these questions. So starting with, what fraction of the 10 rolls resulted in at least 1 6? So each student has done 10 trials, and then they are prompted to combine the results with their classmates and see that more trials can come closer to an actual. And then they're led to make a list of all the possible outcomes. And so this should actually lead them to the need and the desire to be really organized with this list making, and so it's a good place to talk about this table as a good way to write this up. So when you see the table, it's really pretty clear to see which ones have what the possibility of the 6s are, and actually calculate the theoretical probability, and then they can compare and see how close they got with their experiment. And then they answer what fraction would have at least 1 6, so we just saw that. And then they can extrapolate, if they were to roll many thousands of times, what fraction would they expect, and talk about the vocabulary of that being theoretical when they look at a table like this. Now looking back at the waiting times problem, here in the commentary it mentions that students don't yet know the rules of probability for compound events. They're just beginning to touch on that. So a simulation is used to find the approximate answer to these. This would be a really challenging problem for students who do know the rules of probability. And this actually nicely illustrates the power of a simulation. So building a model using these 4 steps is what this is building. So the first step, state assumptions about how the real process works. describe a model that generates a similar random outcome, and then run the model over many repetitions, recording the results, that is, and then write a conclusion that reflects the fact that a simulation is only an approximation. So here, if it mentions using a random number generator, so that can be a dice, it could be using technology. So I wanted to take this opportunity to show a couple of possibilities for technology. In this simulation, there's a string of random integers, and how it was counted was we were looking at, well, what is the wait time? How long does it take before getting to a 1? So if this was the string of integers here, the very first wait time was 2. It took 2 trials, 2 boxes of cereal purchase to get a 1, and then the next one, 1, 2, 3, 4, 5. So we've got 5 for the next one, and so on. So doing 100 simulations and graphing on a histogram those wait times, we see this trend here, and the mean that we find would be 3.8, which is very close to the theoretical possibility. If you calculate that, it converges to 4. You would expect after many, many trials that it would be 4 boxes purchased. And to change it for the second one, we're looking for a set that gives us all 4. So we're looking for how long it takes, how many boxes purchased it takes to get all 4. So with each number representing one of the colors, here we see 4, 1, and then we get a 3 and then a 2. So it took 6 boxes purchased to get that one. And then after that being graphed, we find the mean, and it's very, very close to the theoretical solution. In fact, the theoretical is given here at 8 1/3. So 8.2, very, very close. So if we wanted to set up this using technology, many, I guess most stats classes would use a graphing calculator to simulate something like this. So it's an example of how that might look on a graphing calculator. So if I go to my menu, I'm going to under probability random. Now if you grab a new calculator, you need to seed the calculator. It is random, but it's a computer. It actually uses an algorithm to generate random numbers. So unless you seed your calculators, every student will get the same so-called random number, and it gets pretty confusing pretty quickly. So it's important to do this step if you're ever using a set of graphing calculators to do this. So a great way to do this is to have them type in their phone number or their birth date or something, just so everyone has a different seed. And then back to the menu under probability, I'm going to tell it to find some random integers. So it's got this nice function. I'd like to have the integers 1, 2, 3, and 4 possible. So this is telling the computer to use 1 through 4, and then I can tell it how many I want. So if we wanted to set up the model like we did, like it was explained, I could say, okay, I want 100 boxes of cereal purchased. And then it's listing all of my 100, and I can scroll through and take a look and count up my wait times. Another possibility for this is to, and I've actually done this with classes before, to to set it up. Set it up to go with that first question that we were given. What if what's the chance if I purchase 5 boxes? So if I set it up like this, 1 through 4, I'm purchasing 5 boxes. I'm going to assume that the number 1, the digit 1, represents blue. So in this trial, I didn't get my blue pen. So I try again, I still did not get a blue pen. I try again, still no blue pen. There we have it, a blue pen. So I can click through and do 100 trials here and notate how many of them I got my blue pen and how many I did not. So there's another possibility for setting this up. Now, most classrooms, probably most middle school classrooms, don't have the luxury of having a classroom set of graphing calculators. So here's another possibility. This day and age, you can find just about anything, any kind of app you want for free online. And so here is one that I found that is free, random.org. So we can do a similar thing, generate 100 random integers, the integer value between 1 and 4 for our purposes, for our 4 colors. And then it says how to format it, so 5 columns, that's fine. And then we get numbers. So there is my list, and then I can count up what I've got and build my table. All right. Now on to some more detail on compound events. So kind of a progression of building the idea of compound probabilities of 2 things happening in and kind of situation can go like this. We've got Nina buying fish, and there are 2 types of fish and 4 different colors to choose from, so students can quickly figure out how to build a table like this. And then you can look at, okay, well, what's the probability of each of these outcomes occurring? Well, there is 1 yellow tetra out of 8 total possibilities, so this is a 1/8. And then 1 orange tetra out of 8 possibilities, so another 1/8. And move through, quickly realize that it's each 1/8. Well, looking at this as an area model, we can then point out to students, well, if there's 2 choices on this side here, then this tetra is a 1/2 probability, and the length here is 1/2, and the guppy is 1/2 probability, 1 out of 2, out of this total distance 1. And we can look at this as a 1 as well, 1, and each of these are equal probabilities, so each of these is a 1/4 probability. So if we look at it as an area model, we can see that by multiplication we can also find each of these probabilities, because 1/4 multiplied by 1/2 is 1/8. A next step in this process is here in this problem. If we consider a bag with 2 blue cubes and 1 yellow cube that is pulled out and replaced, and then draw another, we could set up a table looking like this. It's either blue, blue, or yellow with equal probabilities here, or blue, blue, or yellow for the second trial, and these are our outcomes. So we can see here the probability of a double blue, blue, blue would be 4 out of a total of 9 outcomes here. So another possibility of how to set this up would be a more general model, more like this. With the notion that each side length is worth 1 and the total area is 1, we can look at, we've got a 2/3 probability of blue and a 1/3 probability of yellow. So 2/3 times 2/3 gives us the equal probability of 4/9. So if we finish with our blue-yellow 2/9, and our yellow-blue 2/9, and our yellow-yellow 1/9, then they match nicely. To be continued in the next video.